It's time. Okay. My talk is titled Enough TMP to Write a Variant. Yeah, so I heard that this is a good rule, that you kind of give people a link to the slides. So this is the link, it's tinyurl.com, and then it's enough TMP, all small letters, 2022. Okay, so if you want to follow along somewhere, you can. And if you are on your laptop, I will assume that you're following along the slides totally. All right. Okay, kind of like, this is very introductory talk to TMP to some extent, I think. Basically, if you don't know what TMP is Tempate Meta Programming, right? So when we use templates to generate something complicated, right? More than just substitute everything for a type. The most extreme example would be probably Hanna Dushikova's compile time regular expressions. Also, high-frequency traders, like if you've been to previous talk in room A, that was by high-frequency traders. Those people love their templates. There are many applications. In the standard library, there are two. There is tuple and variant. And because they're in the standard library, people do them a lot. I have written a variant, I think, for every standard since 11 in some quality. And so we're going to do variant because with C++20 we can do it in an hour. It's less than 500 lines of code total. Just because probably not everybody is still familiar with std variant, I had the usage here, then it broke, and so 5 seconds before the talk I prepared it again. This is how I was familiar with variant, right? This is an interview problem. Let's say you have Excel. Can you see it okay? Okay. So this is like, let's say you're writing in Excel. And in Excel you have cells. And by definition of the problem, you have, in a cell you can have either an int or a string. And then there's an operation defined like a plus. Let's say you can, int plus int is, int plus string is concatenation. String plus int, you convert int to a string, concatenate. And int plus string, you throw an error. Something like that. Like, again, it's not a real example, it's an interview problem. But this interview problem is much easier to solve if you have a variant, right? So I have a variant between int and a string, and it can be, you can assign to it either an int or a string, and it will keep track of what it is. And then the killer feature of a variant, in my respect, is multiple dispatch. Like, imagine you have to select your implementation not based on one type, like in virtual functions, right? But on two types or on n types, right? And this is standard visit is a way to dispatch on the variant, and it can do multiple dispatch. So I dispatch based on my type and the other type, and I select the appropriate one for the problem. And so this is what we'll do, right? Okay, this is probably barely visible, but what is variant under the hood? It's a union. I'm sorry, but it is a union, right, of all of the possible elements. It has an active index, and then in visit there is some sort of switch between all of the possible types. And we're going to implement all of those components. We're going to start with just a bunch of general purpose template meta programming utilities. And then we're going to use those utilities to build the variant. But first we're going to build up a library a little bit. Let's start here. We're going to find a type by an index, right? Let's say we have a list of types, char, int, double, and we want to find an int in it, right? And where is it? Oh, it has index 1, right? And here, double is index 2. Okay, so how can we implement it? Well, first of all, I'm going to talk a little bit about how do you generally organize your code in metaprogramming. If you do a lot of complicated templates, usually when we want to do something in private, like we'll have either private section of a class, or we will have anonymous namespaces. Both of those things are not available to us really in templates. Like anonymous namespaces just don't work in headers, and Private part of the class doesn't really work with complicated templates because writing friends is really, really hard. So instead what people do is they have namespaces. Andre was ranting yesterday about the detail namespace. Detail namespace is very useful, but the problem with detail namespace is you have one detail namespace per library. And so things in different files tend to clash. So what you do instead, what I recommend doing instead, is having also a namespace per file, right? So here, this would be my file type list, and I have like underscore type lists namespace. This is my convention. This is not very common, but still. Okay, the second convention is like if you want to return, we're going to compute like the index of a type based on in a bunch of types. So we compute something based on types. If you compute a value based on types, the typical interface is you create a constexpr variable, and it has underscore vir in here. So I'm finding an index. This is constexpr variable of type size t. It has underscore v at the end. Right. In order to implement it, I call the internal implementation function. Right. Internal function is a very simple constexpr function. Like this is just an implementation of find. I go through all of the types and I check, oh, is this true or not, and return the index where it's true. The interesting part is here, we for every type in a list, we call std same as and compute basically Boolean value if it's the same as the type or not. Yeah, you can use std ranges find, that's also fine. Then there is a little question, like what do you do when you are like, what do we do if we didn't find the type? There are many options. Then the library obviously returns you the end when you didn't find something. Here I chose to write a requirement that, oh, we have to find the type. So type, I require that type is one of the types, so that the index that we found is less than the number of types. And this way, I can then check for it. Like, for example, I could write a concept, one of, that's going to say, oh, did I find the index? And this is a useful concept. Okay. The next utility we're going to write is uint at least, right? I want to represent a number, and I want to use the smallest unsigned integer possible. Right? So for 100, uint 8 will be enough. For 256, I already need uint 16, that kind of stuff. Similar convention here. If you want to return a type, you create a using type def, right, with underscore t at the end. And this is implemented again by calling a function. And you see this lives in like int utilities file. So I call into int util namespace. The implementation is very simple. It is just if constexpr table. You see, I'm just checking conditions one after another and returning, if it's smaller than uint max, return uint 8, uint 16 max, etc. Okay. The next one is get type by index from a type list. So let's say I have a list int char double, and I want to get second type. That's going to be a double. Right. First type, that's going to be char. This is a surprisingly difficult problem, right? There is a talk by Chris Jusiak, and I believe he will repeat it in the online part at this conference in the track after this, called the nth element case study, where he talks specifically about this problem, how to get a type by index from a type list. The reason why it takes a whole talk for him to talk about this is because it's not trivial to do in optimal compile time. Right? You want, if you are doing a lot of complicated metaprogramming, like they do in HFT, you care about that. Here I talked to Will Ray on CPP length Slack, and we both agree this is reasonable. How I'm going to do this? I'm going to just have a constexpr table. Okay, we're going to unroll first 10 types. And if the type is index is 0, we're going to return the first type. Index is 1, returns the first. You see, like you see zeros type, first type, etc. And if there's more than 10 types, we're going to recurse. This is why I'm not just doing if n equals 0, otherwise recurse. Why do I do unrolling? basically, generally speaking, the performance of your compile time should depend on the number of instantiations. And so if I just did one if else, then I would instantiate the function for each of my types. This way, however, I instantiate only like for every 10 types I instantiate a function. There's another interesting thing here. You see, in the previous function, when we returned the type, I just constructed, default constructed it. But in general case, you can default construct a type. So we need to wrap it into something. And we wrap it in the standard type identity with just an empty struct with a type definite. Yep. The next one is instance of. Right? We want a concept that will tell us if something is an instance of certain template. Like vector of int is an instance of vector. But int is not instance of a vector. And a little bit of a tricky one, vector reference is not an instance of a vector. Maybe. We'll talk about that in a second. How do we do that? Well, okay, this is a concept, and the concept just calls into implementation, right? Implementation is done here with a template specialization. I have a default case. It's going to say no. And I have a specialization that is going to say if it matches, like, you know, if this is a template what, and this is an instance of a template what, this is going to inherit from true. So standard false type and standard true type are just structs with a constant. Like, so you see I get the value here. And this is what they provide. It's just an empty struct and has inside value equals false or value equals true. Yeah, they just come in as handy. There's one caveat with this. At instance of only, you cannot write a general purpose instance of in C++. So because you have either type name template parameters or you know, value template parameters. You cannot have either or. So in this case, I only need type name template parameters. That's going to be enough for me. That makes sense? Perfect. You're going to nod for me. All right. Next thing, forward. I believe this version I took from Jonathan Muller's blog. We all know how to forward, hopefully, right? You do standard forward, you know, if you t x. This is unpleasant because you need to know the type of t. So sometimes you have to write std forward decal type of x, x. Surprisingly, this works. Like, but this is also, this is really annoying to type. So people use a macro, right? And this is how that macro looks. So you have, it's a static carp to this decal type is effectively forward, but in line, so it's faster to compile. And here's a dot, dot, dot trick is also really cute. So like if you work with gtest, you know you have to put braces around things sometimes because it interprets commas as part of the macro commas and not your expression commas. Well, what this dot, dot, dot does, it basically says, yeah, treat them as macro commas, but then also unpack them all together. So if you have a macro with one parameter, this is a cute trick. Okay. And with this, I'm ready to do a union. If anybody has any question, I can try to answer that. Okay. So union is something where we're going to store the data, right? It's similar to C++ standard union, but built-in union, but you cannot unpack into a built-in union, so we need a little bit of support. Like you see union underscore in char double, and I can construct, construct me the second element. You know, it's a double. I can get an element from there. Destroy, construct the first element, and destroy it. This is tests for get. Let's start at the end. So how do I write destroy? I call std destroy at, and I get the address. And how do I call construct? I would like to do the same thing. Unfortunately, it doesn't work. There is std. So instead, I will have to write a constructor. Right? Std construct at and std destroy at are super useful primitives from C++ 20. They allow you to do placement new effectively at compile time. You cannot do placement new at compile time, but this one works. Okay. let's look at the union itself. So we have it's done as a recursive. Okay, there is used to be for a while people did buffers. So people just created a bunch of chars, and they were like, okay, this is going to be big enough, and we're going to cast pointers to the types we have. So that was implementation in 11 and 14. But that's not constexpr friendly. You cannot cast pointers to buffers. If you want to see that solution, there is a Stack Overflow post. What people do now is they unfortunately have to recurse. So we have a union that stores a union, head, tail. And then we have a default case with one parameter that just has a head. I mentioned that number of instantiations is important. Maybe you could have done here like, T, T0, T1, T2, T3 to reduce the number of instantiations, but I wanted something reasonably simple. Okay. So there is a default constructor, and then there's a constructor for the head. So you see I'm passing the index in this standard wrapper, saying, oh, okay, construct me the zeros index. This is just how you pass compile time parameters. You have some struct, you have a template parameter with the parameter you want, and you pass it in. In this case, this is standard in place index t. And then I have, if it's not the zeros index, I would like to construct whatever the next index is. I pass it along to the tail, basically. There is union size, just to tell me how many elements are in the union. Yeah, it's again very simple. It's done with this template specialization. I have a base case, and then I specialize it for a union. And here I say, oh, okay, size of TS is going to be my template union size. And get. So get, the implementation of get is very simple, right? If it's 0, forward, get head. If it's not 0, get tail. That's it. You see we're using tools forward, and this becomes very clean implementation compared to me having to do all the forwarding myself. The tricky part is the requirement, right? Why do we want requirements? Well, because everybody has a get, and your gets will clash, so you really want to have some sort of constraints. So this is only this get matches. In theory, I could say, right, instance, of union. That would be my expectation, that I could have said that. Unfortunately, this will not compile because of how perfect forwarding works. Nico mentioned that as his keynote yesterday a little bit as well. Basically, self here will deduce not as a union, but it will deduce as union reference sometimes. So this is a big kind of controversial topic. Like standard ranges concepts like forward range and forward iterator, they will eat up references. Standard, regular type will not eat up references. Which one is it correct? I don't know. Sometimes I remove reference in my concepts. So here I didn't, and this is why I apply instance of to removing reference, type name. Yeah, this is why I apply instance remove cvref when I do instance of. And the second requirement is, yes, that basically index is less than union size. Okay. Thank you very much. All right. If that makes some sense, we're going to go and do a switch. All right. Again, we would like to unpack into a switch, but that's not possible. So this is another important template metaprogramming technique. Because in all other cases, the code gen would be identical, regardless of whatever technique we do. Here, depending on how we write implementation of our compile time switch, like the result will be different. So we want to understand what assembly we get in the correct case, and then we're going to try to match it. Right, so this is a kind of correct case, and what do we see? We see a jump table specified, and basically, we compute the index and then do jump to the correct position. So this is what John would like. Let's first figure out the interface that we're going to have for our switch. Right, you see, I have the switcher class. And switcher class accepts how many cases we have as a compile time parameter, right? I have a parameter here, and it accepts kind of the number of cases at compile time. And then it has a lambda for each of the cases. where the label of the case is accepted as well as compile time parameter. Right? And then I'm going to call it with a runtime index. Okay. So how do you pass compile time parameters? Well, I have a struct. It has a size t parameter in it. And I have compile time value to generate the struct just for, I guess, cleaner interface. I could have gone and did auto here instead of size t. But then what comes is that because compile time doesn't like to do conversions, and I really want size t, I don't want any other type. You have to basically, in all invocations, make sure that it's going to be size t, so it's annoying. That's why I chose to go with size t here. Let's look at kind of like implementation. So we have a struct, and you see here I don't pass any compile time parameters. But nevertheless, switcher is a struct. It's not a function. How does it work? It's CTAD from C++ 17, compile time argument deduction. Right? I have a constructor with two parameters, size and operation. Right? And even though size is not used anywhere here, it matches against this parameter. And that's why C++ knows that this is a parameter I want. The result type, I'm not doing anything fancy, just the result of the first case is going to be the result of my switch. And the implementation. And I'm going to skip this one. I took from Mikhail Dominic in variadic expansion and examples. The reason we're going to skip it is because it's not going to give us the result we want. It's doing an array of function pointers. And it is jumping to the array, to the appropriate function pointer for the case. However, you can see that there is a call, and this is not what we want in assembly, so this is not what we're going to do. A second implementation is, I learned from Sean Baxter, that Clang and GCC can optimize a sequence of ifs into the correct solution. So we're going to generate a sequence of ifs, and we're going to generate it with a macro. I'm sorry. Basically, the macro has two cases. Like it has if constexpr check first to make sure that we don't try to call something that doesn't exist. If we set 10 cases, we don't try to call it with more than 10, right? And then it has a runtime check. And then I have 10 cases, and then I have 100 cases, and I'm going to, do 1,000 cases, and if it's more than 1,000, recurs, right? And this will generate me a jump table. I'm not going to make it look through it, but it's not going to be the same as the switch, just not quite matches. And the compiler generates that one for the switch. So the one I actually go from, I take from this Groundswell audio GitHub. And this is actually a switch. Just basically, we generate a case with a macro, right? And we're just going to spam a bunch of cases in a switch. Yeah, don't forget to undef your macros for things like that, just so they don't pollute a namespace. Can you nod? Thank you very much. Okay. So with this, we kind of build up a little bit of tools to do the visit itself. Let's see how this looks. What are we trying to do? So, as I mentioned, private doesn't really work for templates. So what I'm doing instead is I have a details namespace here, and I do all the things there, and then the privates and the accesses and all that stuff is going to be in like surface layer. So I have variant data, and it has index. And index is at least this many types. We had this utility, uint at least. I have the size here to help me know how many elements. Union is to store my data, and then index. There's a little bit of a question, what do you put first, like the data or the index? And the reason why I think you should put the data first before the index is that index is very likely to be like a byte. And so it's going to mess up your alignment. And basically you will have a giant gap between like index and the data. Right, let's skip all of the noexcepts and results for now and just look at the runtime code. This is our switch, right? We have computed how many cases are going to be in a switch. Well, we had a bunch of variants. Multiplication of sizes is going to be the number of cases we have overall. For each case, we need to convert, like, okay, imagine we have like 5 variants, but switch operates on one case, like it goes 0, 1, 2, 3, 4. So we need to convert that, 0 into 5 indexes. So first element will be 0, 0, 0, 0, 0, etc. 0, 0, 0, 0, 1, etc. Right, so there is a class that does it for us. And then we call for specific case, right? There is a little bit of a trick here. So like you see, we call the switcher, right? The trick is that in this specific case, we need to check if the result type is void, and if it's not void, we cannot return. In this specific case, this is just one of the C++ weirdnesses. Okay, so basically, let's look at this mass class. Like, how do we convert from one index to many indexes? It's actually the same logic that you would encounter in C arrays, right? So like you have array with 3, 4, and 2. This is actually a linear array. And so I basically implemented the same logic only myself. And I, check that everything matches. Yeah, so like this is like the math. Just I convert from from a scalar index to array of indexes, and from array of indexes to scalar index. This is not very interesting. What's interesting is how do you apply? You need to apply for like every element in the array. You need to get an element, do template meta programming with arrays, and you can't. So here we actually using std index sequence. Right, index sequence is this type that has a bunch of parameters, like a bunch of indexes right now. And so like it's going to be, we're going to convert an array into this array index sequence. How do we do that, right? So this is a standard trick. Like what you do is you write your array of indexes into a constexpr variable, right? That's the first thing. And then what you do, you unpack for every element in the array. Because it's a constexpr variable, you can now access it in any template you want. So you unpack that array of indexes. Like you create an index sequence, 0, 1, 2, 3, up to size of the array. And then you return the index sequence where you get the element for every index. So, okay, this is going to be index sequence 0, 1, 2, 3, up to size of the array. Then I'm going to return an index sequence is going to be array zeros. So like A0, A1, A2, A3 in an index sequence. And now I can mess with it. I can do all the template meta programming against it. Specifically, I can unpack it into this, and I can then use it into when getting index from variant. This is probably the most complicated thing here. Kind of have a look at it, if it makes some sense. Index sequence is array or is a sequence of numbers, just a template. I unpack over it. So this is I'm going to create get the first element from the index. This is from the first variant. Second element from the sequence from the second element, and so on. Okay. If it's still confusing, like there's going to be an example to unpack a tuple on CPP reference. Look at that. Finally, that kind of deals with runtime. Now we just need to do the return type and the noexcept. And we want to be able to check in concepts that we can visit things. So this is, I don't know how well understood it is. But okay, let's see. So let's say I have a concept. So I have a function call foo, right? And it's just going to call x.foo, right? And I have a concept, can call foo, that calls foo. Right? Makes sense. All right, and I have a struct, and it says can call foo, and compiles. I can make it bigger if it needed. Okay. All right. However, if I type an int, it will also say compiles, right? Despite int not having foo. The thing is, right, that concepts and everything like that is checked only at the signature, right? And So like for example, one way to make it work actually. So this is what's not concept friendly, right? Because concepts will not detect that this doesn't work. So if you want to make call foo concept friendly, right? You need to, for example, specify in the requirements that you want this to x.foo to work, right? I say has method foo, and now it works. Or this is preferred, right? Or I can mention it somewhere in the, let's say, return type. That also works. So let me say decal type x.foo, and here I'm going to say auto. And, well, I should return probably, right? This also works. It says, oh, it cannot call foo. It can. However, what happens if I just say auto, right? It should compute the return type. Well, in this case, this becomes a hard error. This is not concept friendly. Right. So you basically, if I write it like this, with just auto, without mentioning in the signature any parameters, all right, then you will have a hard error, even if you try to check that it works in the concept. This is done for you to avoid kind of silly bugs. If you made a typo in the template and you have a default implementation, right, you don't want that to suddenly work with default implementation. You want to get the bug. Before C++, like concept friendly is my term. Official term that everybody uses is sfinae friendly because this is what how this works. How this used to work, especially before 20. Okay. So the problem with concept, like if we try to specify this with concepts, like if we try to specify requirement as concept for a variant, it doesn't work very well. I couldn't get a very nice error message. So I'm going to show you a different way to do it. We're going to have a common type utility. Basically very simple, like, a common type between int and double, that's a double, right? Common type double int, that's still a double. Common type between string and int, what I'm going to do here is I'm going to return this weird thingy called no common type, right? And what this will give me is when I have a function that returns like whatever this thing, right? Common type, it's going to report me an error. Sorry. Well, you cannot see this, but it says tools no common type int basic string. And this is one error line. So utilizing named return parameters to indicate errors is a very powerful technique to give your users nice error message. How does this work? Well, I have just non-common type. This is just a weird, simple thing. I have a concept called error tag. It requires if t has an is error inside. And then what I can do is, if one of the common types is error, right, then I'm going to return that. Because let's say something inside of it failed, like one of the variants couldn't compile, one of the visits couldn't compile, right? Otherwise, I'm going to try to, if there is standard common type, to compute the common between all of them, I return that, and otherwise I return no common type between all of the errors. Now let's do one case. So we're going to compute the result for one specific case. Let's say I have two variants between A, B, and C, D, and I have a visitor, right? And like in the zeros case, like between this one, right? So when it matches 0, 0, it should return me A ref, right? And so this is 0 case A ref. In the first case, it's going to return it's noexcept. It also returns me if there is noexcept or not. Okay, so how does that work? Well, basically both result type and noexcept are derived from one common struct. All right, I just call a function and it returns me a struct that contains both of those information. Right? What does a function do? The function uses so okay, like we had V1 and V2. We want to get A and C, right? This is what we wrote the mass transformation for, like get me 0, 0 index, right? This is what we do. We unpack that, we get those 0 and 0, 0, and then we send it into a struct. that is specialized. In the default case, it's going to return like no invocable type. And when it is invocable, then I'm going to return invoke result for the return type. So yeah, and then in the default case, noexcept is false, and then if it is invocable, then the noexcept is actually computed correctly. And now we can do the overall visit. So let's see what I talked about with error messages, right? It says cannot call visit, whatever, substitution failure, not an error, blah, blah, blah. And it says not invocable, and then it tells me this is my lambda, this is the first parameter, this is the second parameter. I'm really sorry you cannot see it, but trust me, it says it's there. Okay. So the noexcept is very simple. Like if all of the cases are noexcept, then the result is noexcept. This is just an unpack with end. That's it. The result is using the common type. So we take, for all of the cases, we compute one case result, and then we throw it into common type. And then we check, oh, if it's an error tag, then return it. Otherwise, wrap it and return. Yeah. And finally, we need to wrap this. This is the detail stuff. So we need to put it inside of a variant itself. So how does that look? Sorry. So this is where we do the private stuff. Like, so we have variant, and in private there is data. In order to, how do you get the data from here, right? Like, so I mentioned writing friends is hard in templates. So instead, what I do is I have the, my detail namespace underscore variant, where I have get data with no concepts. That is very simple, and I'm gonna friend just that, right? Okay, so constructor. How do we construct? We find an index of a type, and we constructed that index. We assign that index. How do we copy? We do a visit for detail stuff, right? How do we destroy? We do a visit. And finally, how do we visit? We do a visit. There is all of the requirements, right? So we need to, what are the requirements? Like all of the variants should be an instance for a variant. That's the first thing. Then noexcept is, I'm writing noexcept here as if the detail is noexcept call, because that is computed correctly using our tools. And the result type. Is I have to duplicate here the same thing I wrote in the detail to get the nice error message, right? So it again works. I have here if 0, one sec, where is it? Yep. It says variant no type, non-invocable with the lambda and the parameters. It says, so there are other things I did, like this is again URL to the slides. I'm one of the maintainers of ifsimd library, if you want to check that out. There is a talk by me and Joël Falcou. There are a couple of introduction to SIMD talks by me. And there's my email and Twitter. And this is, hopefully that works. Yep. This is all tests. And this is the implementation of a variant and less than 500 lines of code. And with it, if you have any questions, I'm happy to answer. Like, hopefully you were lost, like, closer to the end.
I'm wondering what the debugging experience is like for debugging these things. Can you speak to that at all?
Well, you can put a breakpoint inside a lambda, and then you will see, I don't know, let's see, you will say details visit, let's say, and after details visit, you will see the switcher, and then you should see your lambda. Right, so it shouldn't be too bad, especially with like hide my stuff. What's the Visual Studio debug thing that says hide only my code? There's a Visual Studio debug thing that hides the implementation details.
And for the compile time only parts of this, though, you can't use a debugger. Right?
For miserable. That's a debug experience.
Right, it's more what I'm talking about, yeah. Do you have anything for that side, or is it just cry?
No, but I think that if you get, so like the one line, the point of error messages, like trying to generate the small error message is specifically for that. Like, so there was a lot of effort to try to get you like one line that says what's wrong, because other approaches will give you just like everything is wrong, or like it will say like just a giant stack trace if it's not constexpr friendly. You can also static assert. That's a very reasonable thing to do. But that's not going to be concept friendly. Like then you cannot check whether something is invocable or not, which is reasonable, which is a reasonable thing to do for your code. But for something like a variant where it's very general purpose, probably you want to be concept friendly and noexcept correct.
Okay. Thanks.
Okay, we all just got 5 minutes back. Thank you for coming.